Hello students, this is Dr. Gerstmann. I'm making this recording for you on Monday, I think October 8th, 2012. This is a brief presentation. It's a supplement to your main Chapter 5 PowerPoint presentation, and I thought I'd take this opportunity to try out this new software I have that will upload presentations with VoiceOver to the web. So as you can see here, this is two additional examples of categorical data analysis for two-way tables. I first want to address exercise 5.6 that you have for homework. I'm not going to go over the entire homework example, but I do want to point out some things in this table. These items on the bottom are, let me get a felt tip pen here. These items on the bottom are just for my own, so I don't forget to mention anything to you. And the first thing we must always mention in any type of statistical problem is state the question that's being addressed. So make sure you read the question on page 123 very carefully, and after you do, I'm sure you'll recognize that the two explanatory variable for this problem is different types of delivery of vaccine, and so that's in the rows here. So we can call this variable anything just for convenience. Let's just call it vaccine delivery, so it'll be easy to refer. See that the vaccine delivery variable, the explanatory variable, is in rows, and we should be aware of that when we get to address a question: is there an association with the type of delivery system and the immune response? So the response variable here is clearly in columns. I'm going to distribute a press release that's the source of this information, just a handout. Okay. The other thing I want to discuss here is the data as presented in the textbook does not include the marginal distribution, and sometimes you get a table that already has the totals calculated for you. I'm just looking at table 5.1 that already has the marginal values, but as I look at the table on page 124 in your text, there are no marginal values. Now sometimes I'll just put these in routinely because they're often so they're needed so often. So for instance here, it's just nice to keep in mind that there were 8 people in the first group, and then 8 in the second group, and 8 in actually all the groups. So the row totals are 8, 8, 8, 8, 8, and the table total is 40. Right? We can go further if we want. We can see that 16 of the study subjects had a positive immune response, so that leaves 24 that were not. Okay, so now the thing to just keep in mind is the proportion that you calculate will depend upon what question is being asked, and so we can ask many types of questions of this data. We might ask how many people total were studied. We might ask what is the overall immune response rate for all 40 subjects combined, which of course in this case would be, just as an example, so that 16 of the 40 subjects had an immune response. So what is that? Let's see. Maybe I better use my calculator so I don't embarrass myself. 16 over 40 is 0.4. So as I impress upon you, just so that just it's a good habit to carry extra significant digits. So as routine, we carry 4 significant digits to let us know that this is accurate to 4 significant digits. I'll write it as 0.4000. Now, the other thing to keep in mind that's not in the book, but I'm going to emphasize here, is that San Jose State uses a reporting style for text and for numbers called APA, American Psychological Association's reporting style. And so in this particular reporting style, they like proportions to be reported as percentages with 1 decimal place. So let's report that as 40.0%. Okay, so that's one question we may ask of the data, but ultimately I'm not sure if it's in 5.1 or 5.6. We're going to have to ask which one, is there an association between vaccine delivery type and immune response? So, okay, I already did APA reporting here. So to do that, well, the proper conditional proportions, let me just write that here, or conditional percents if you like, depending on if you're working with decimals or percent values. those are going to be the row proportions. So that's pretty easy to calculate here. Now you can do the row proportions for both categories of immune responses, but I'm just going to look at the percentage in each group that had an immune response. So that makes a lot of sense since the explanatory variable is in rows. For group 1, that's 0.2 milligrams of vaccine divided by electroporation, and electroporation I read up is a type of vaccine delivery with electrical impulses. It's supposed to give you a better response to the vaccine. So in group 1 we have 3 out of 8, right? And so just following our reporting standards, 3750 with 4 significant digits, and for APA reporting 37.5%. Right? And so we would continue with each category. Sometime you'll see in a professional journal, they'll report the percentage and percentages, and because it gets a little crowded to write percent there, they'll just sort of in the column heading put a percentage in parentheses so you know that these refer to the percentages. Right? So if you do that, those conditional proportions, you'll be able to answer the question, is there an association between the vaccine delivery type and immune response? And then as we're prone to do in the class, we want to then convert that conclusion to plain language in its real world setting. The second example I want to provide you is another example of Simpson's paradox. It says a new example of Simpson's paradox here, but really that's false advertising. This is the textbook example in chapter 5. The more examples you can work through, the better off you'll be. The textbook has many excellent examples, and my PowerPoint has additional examples. So by the time you get to a problem in the homework, if you can recognize it, you've actually seen 2 examples. Now, the problem for some students is recognizing it because it may be presented in a different format or with slightly different words. So in this example, we're going to see whether the helicopter evacuation from an auto accident is better by a road ambulance, highway ambulance, or sometimes they'll bring in a helicopter to fly you to the hospital. So that's the explanatory variable, and we're going to just look here at whether the study subject survived or died. Now, whenever you look at any research problem, whether it's in Chapter 5, Chapter 4, Chapter 3, whenever you look at a relationship between an explanatory variable and a response variable, we must always look to see, or we must always consider whether lurking variables may explain any potential association. So of course we know that is called, that calls into question a phenomenon we call Simpson's paradox, where the explanatory variable sort of changes the direction, or the lurking variable, changes the direction of the association. So I believe the textbook does this very good example of Simpson's paradox with helicopter and road evacuation. I see that this is exactly the same numbers presented to you on page 129 of the textbook. So instead of sort of going through it in as much detail as the textbook, I'm just going to remind you that when you look at all the data for helicopters, that the risk of death, again the explanatory variable in this problem is again in the rows, so the conditional row percent for risk of death for helicopter evacuation is 64 over 200. So 32% of the study subjects evacuated by helicopter died. In comparison to for the road evacuation, we have 260 deaths over 1,100. So we have 23.6% of the road accidents had died after their accident. Now, does that mean that there's a positive association between helicopter evacuation and death? Well, there is an association, but does that mean whether helicopter evacuation causes death? And of course, unless you have the little tiny brain of Homer Simpson, then you would recognize that that's sort of a silly conclusion, or at least not a very plausible one. So what do? You consider the extraneous variable, or the lurking variable of severity of accident. And for this chapter anyway, a good way to look at the effect of the lurking variable is to stratify the data according to accident type, so analyzing serious accidents separately from non-serious accidents. If you read through the exercise on, not exercise, but example 5.6 on page 129, you'll see how when you look at the accidents separately by the lurking variable, that you'll have for helicopter 48 of 100, 48%, right, versus 60 of 100, showing here that the helicopter evacuation cut down on deaths, right? And same thing if you just look within the non-serious accidents, you have 16 over 100, which is 16%, versus, right, just marking them off here, versus 200 over 1,000, right, which right is 16% versus 20%. So once again, you have some a negative association between helicopter evacuation and death. So I hope you found this recording useful. I know it's rather amateurish, but it was my first go with this technology, and I'm sure I'll get better over time. Thank you very much.